gave a great synopsis of three important arrows. So the epistemic arrow, the thermodynamic arrow, and the causal arrow. But there's one other arrow that I wanted to ask about. So granted, Barry, as you put it, we don't know the fundamental ontology of the world yet. And in David's vernacular, this is a big slot that needs to be filled. And the quantum theories aren't complete. But the arrow that I wanted to ask about was wave function collapse. And even you also mentioned Sean Carroll. So even many worlds advocates, even if they don't believe that the wave function collapses, there's still a temporal asymmetry here. And I'm wondering how or if the Mentaculus has anything to say about this sort of quantum
Yeah,
arrow.
sure, sure. First thing to say is if there's such a thing as physical wave function collapse, say as in the GRW theory or something like that, then the Mentaculus has a slightly different structure. Then you won't need then you won't need a statistical postulate. You'll just need the dynamics, which has chances in it already, and the past hypothesis. You might think that so there are two interesting features to point out about the collapse of the wave function in something like the GRW theory. One is it involves dynamical chances. The other is it's not, the law is not time reversal symmetric, like the laws. Yeah.
Yeah, I was just going to say, I don't think that all of our listeners know the GRW, Gard Rimini Weber theory. So maybe just like in a minute, you could say what it is.
Um, um, there is a problem at the foundations of quantum mechanics. I would say, this reminds me, if I can just digress for a second.
Please digress.
I had to talk to my son's sixth grade class many years ago now. And as I walked in, I was going to talk about actually some things about time, which I thought the kids would be excited about, maybe time travel or something like that. And as I walked in without any warning, the sixth grade teacher took me aside and said, you know what, if you could begin with just a 5-minute little summary of what philosophy is, that would be great. Okay, that's something comparable to what you've just asked me to do in 5 minutes about the GRW theory. It actually went okay. I won't say what I said, but anyway, there is a puzzle at the foundations of quantum mechanics called the measurement problem, which I and most students of the foundations of quantum mechanics regard as the sort of central problem at the foundations of quantum mechanics, which is that quantum mechanics, as it's standardly formulated, gives us probabilities of how a given experiment on a given precise macro state of the world is going to come out, okay? The trouble is, so it gives us a certain probability associated with the outcome of the measurement being A, and a certain probability associated with the outcome of the measurement being B, and a certain probability associated with the outcome of the measurement being C. The trouble is that I don't know how to put it. Quantum mechanics, as it's usually formulated, is profoundly opaque about how it is that one or the other of these outcomes actually manages to manifest itself in the world. The standard quantum mechanical picture gives us a superposition of these three outcomes. And if you just apply the fundamental quantum mechanical equations of motion to the measurement process, what those equations of motion are going to tell you is that you're going to get a result which is a superposition of the measurement having come out A and the measurement having come out B and the measurement having come out C. That's, of course, not what happens when we do it in the laboratory. God knows what that would even look like. Okay. Our experience is we either get A and we get that a certain percentage of the time, or we get B and we get that a certain percentage of the time, or we get C. And the basic equations of motion of quantum mechanics don't give us any hint of, as it were, how that transition from three possibilities to one actuality takes place. Okay. And in order to give a coherent picture of that, various solutions to the so-called measurement problem have been proposed. One of those solutions is that every now and then, the wave function, for an instant, stops evolving in accord with these fundamental equations of motion and involves instead in a chancy way, which in these sorts of circumstances will produce either A or B or C with the appropriate probabilities. Okay. And the way you have to modify the equations of motion in order to get a theory like this involves introducing into the theory two elements that weren't there before. One, genuine chanciness, because the Schrödinger equation, which is the fundamental dynamical equation of quantum mechanics, is completely deterministic. It, in a deterministic way, gives you this superposition of three outcomes, which you don't know what to do with. Good. So getting one or the other of these outcomes to emerge, using this particular strategy, this strategy of so-called the collapse of the wave function, is going to involve modifying the fundamental equations of motion in ways that involve introducing both genuine physical chances and time reversal asymmetries, neither of which are present in the Schrödinger equation. Good. So you might think that in particular, these time reversal asymmetries that you have to introduce might, in addition to solving this measurement problem in quantum mechanics, be what lies at the bottom of all these time asymmetries: the thermodynamic time asymmetry, the epistemic time asymmetry, the causal time asymmetry. It is, after all, now an asymmetry, a time asymmetry in the fundamental dynamical laws of the world. It turns out, if you do the analysis, that although the chanciness may be able to take over the full job of the statistical postulate, okay, in the earlier version of the Mentaculus, the time asymmetry involved in the collapse is not going to be able to take over the full job of the past hypothesis. You're still going to need a past hypothesis in order to account for the thermodynamic and epistemic and causal differences between the past and the future, even in the context of this kind of chancy and non-time reversal symmetric theory of the collapse of the wave function. Okay, so it turns out, I don't know if that's enough of an introduction. If you want to ask me a question to clarify it further, by all means, jump in.
David, make it clear that the Humean metaphysics is an orthogonal issue.
Yes.
Your
absolutely.
Theory is
These chances, metaphysically speaking, are just like the probability distributions over initial conditions. Yeah, thank you, Barry.
And within the Everett account, which I know that Robinson has got podcasts about, they have a real problem, as you've pointed out in many articles or discussions, with what to say about probability. And then you have to have a whole other different kind of story about probability.
Right. But so anyway, in in the GRW, if you were to adopt a GRW style theory of the collapse of the wave function, it turns out you could get rid of then the statistical postulate. You can't get rid of the past hypothesis. Many worlds, insofar as it's coherent at all, and as Barry mentioned, I have worries that many worlds is just not coherent because it can't produce an account of what quantum mechanical probabilities are about. But if you were to imagine that it's coherent, then the way the Mentaculus is going to work in the many worlds interpretation is very similar to the way it works in classical statistical mechanics. You will need, it'll have exactly the same structure. You will need a statistical postulate and you will need a past hypothesis, in addition to the microscopic equations of motion, which in the case of the many worlds interpretation is going to be just the Schrodinger equation. That is, the many worlds interpretation attempts to take this, this lemon that you're getting in quantum mechanics, that the measurement is going to produce a superposition of three outcomes and turn it into lemonade, okay, by declaring that no, there really are these three outcomes, and we're stuck in one of them. And that's why it appears to us as if the experiment has had only one outcome, when in fact it's had three. Okay, like I say, whether or not one can, at the end of the day, coherently make sense of a picture like that remains an open question, and I myself have doubts about.